Hello students, today we will discuss divergence of vector field. Here we will do it in two part. One is its mathematical representation, and then in the second part we will discuss its physical meaning. Okay, and to understand both these things we will make use of Gauss's divergence theorem, and Gauss's divergence theorem connect the volume integral divergence of the vector field over a volume V enclosed by a closed surface S and the surface integral of the vector field. Okay, so this is how we represent Gauss divergence theorem. Okay, so here the vector field is electric field, and what does this flux represent? This is electric flux which you have done in 12th standard, and it gives you the number of field lines passing through a surface area. Okay, now we will see how these number of field lines are related to this divergence. So firstly, come to the first part, that is mathematical representation. So here we have taken electric field intensity E as vector field, and it is a function of coordinates x, y and z. So it is independent of time. As the coordinates changes, x, y, z, they change, then the value of the magnitude of electric field will change. Okay, now come to mathematical representation. So if we have electric field E and we are to find its divergence, then we will put the operator del before it and take its dot product with the vector field. Okay, so if you write electric field E in rectangular components, then you can write vector E. This is x component of electric field, then its direction, then its component along y direction, then component of electric field along z direction. So this is how you can write the vector field, vector E. Okay, and now we are to find its divergence. So this operator del, you can write the operator del as del, this is curly by curly x I cap plus curly by curly y j cap plus curly by curly z k cap. And if you take the dot product of del operator with this one, this electric field, then you will get the divergence. Okay, so if you take dot product of these two, then you know in dot product the corresponding components get multiplied. So if we have vector A and B and you find their dot product, then the corresponding component of A and B along x direction, they get multiplied, and you are to sum all these products. So the next will be AY into BY, then you have AZ into BZ. Okay, so if you simplify this, then you will get curly by curly x of vector and its component along I direction, that is Ex, and here you will write curly by curly y of the y component of electric field, and then curly by curly z of the z component of electric field. So this is how you can write, you can mathematically represent the divergence of a vector field. Now we will discuss what is the physical meaning of this divergence of the vector field, and for that we will find this flux, okay, and we will conclude finally that this flux is divergence of the vector field. Okay, so if you simplify and take idea of definition of the divergence of the vector field, so you see, if this is the divergence, and then you can write it divergence of vector field, this must be equal to, this is the flux. So if you write it here, flux of the vector field divided by what is this? This will be integration of this volume element will give you the volume. So simply divergence is flux per unit volume, flux passing out per unit volume. So we are to show this thing. So the next part is the physical meaning. I have told you the physical meaning, and we will do mathematical analysis of this thing. Here we are to discuss now the physical meaning of divergence of the vector field, that is electric field. The vector field here is electric field in our case. Okay, and we have a point here, this is x direction, this is y, and this is the z direction, and here we have a point P, and the coordinates of point P are x, y, z. Coordinates of point P, these are x, y, and z. So this is the location of point P, and this point P is at the center of a cuboid. So let me make a cuboid here, and this is how you can represent. Okay, now suppose the electric field, the x component of electric field is along this direction. Okay, so this is Ex, and we will take here, and this point P is at the body diagonal, at the intersection of body diagonal of this cuboid. Okay, now we will consider this cuboid, which is made up of 6 faces, and we will find the flux, the total flux diverging out of this cuboid. Okay, so you can see here, if we take this top face, its normal will be along this direction, and the x component of electric field will be along this direction. So you can see the angle here will be 90 degree. Okay, so we can say, if we find the flux for this face, then it will be E dot ds, and if you open it, then you will get E ds cos 90 degree, and cos 90 degree is 0. So you can see this face will not contribute to the electric flux with respect to x direction. Okay, component of electric field along x direction will not, the field lines along x direction which are along the x direction will not penetrate this surface. In the same way, the surface which is in yx plane, that will not contribute to the flux. Okay, and the surface which is in xz plane, mean to say this surface, this will also not contribute to the electric flux. Okay, so if we find the electric flux with respect to this component of electric field, then only two surfaces will contribute, and one is this surface, you see, one is this surface, okay, and another surface is this one, you can see, okay, and the electric field at this face is towards positive direction, and here the electric field is along this direction, and at this face the normal is along this direction. So you can see at the second phase here the normal to the surface and the component of electric field, those are in the same direction. So here the angle between the x component, okay, the angle between the x component of electric field and the normal, that is 0 degree. So here the angle is 0 degree, and at this phase the electric field, component of electric field, that is Ex dash. Let this is Ex dash. Let me write it here. This is Ex dash, and the normal is along this direction. Okay, so here you can see these are in opposite direction. So here the angle theta, it will be pi. Okay, and if you find the electric flux here, then it will be the electric flux E dot ds with respect to x component, okay, or the closed surface S enclosed by the surface area of the 6 faces, that will be due to this first phase and this second phase. So you can write this is Ex. Now the value of Ex at the first phase, that is Ex1, okay, into dot ds, okay, dot dx, and plus I have opened this closed surface, and this closed surface S is composed of 6 faces, and we have discussed out of these 6 faces, 4 faces do not contribute, their flux is 0, and we are left with these 2 faces, and we are to discuss them here. Okay, and the another one is E double dash x dot ds. Okay, now you have to solve these things. Ex1, this is the value of electric field at the first phase. Okay, so we are to find this, then we will see what are the dimensions to find the surface, then we will see what is the angle between the component of electric field and normal to the surface. The same things we will do in the second term. Okay, so here if we assume that this is the point P where the coordinates are x, y, z, the value of electric field is Ex, y, z. Okay, and we are talking of the x component, the value of x component at the center point, that is P, that is Ex, and here it is Ex1. So to find the value of x component of electric field at the first phase, you can make use of this thing Ex dash. This is rate of change of x component with respect to x, and now you are to find what is this gap, the gap between the center point and the first phase. So if I assume that the dimension of the cuboid, that is dx, and this is the center point, mean to say the gap between the center point and the first phase, that will be dx by 2. So here I will multiply it by dx by 2. Okay, and if you want to find out the value of the x component at the second phase, then it will be, okay, one more thing, this is the change, okay, this is the change, and you have moved in negative direction, and by how much amount? Dx by 2. So you will put a negative sign here because you are moving in negative x direction. And what is the value at p point? This is Ex. Okay, in the same way, to find the value of x component of electric field at the second phase, what you will do? You will write the value of Ex component of electric field at point P, and this is Ex. Okay, and then by how much amount this component changes when you move to the second phase? This will be curly Ex by curly x into plus dx by 2. So plus dx by 2 is the distance you have moved from the midpoint to the second phase along positive x direction. That's why I am putting here plus dx by 2. Now we have calculated the value of Ex1 and Ex2 at the both phases, and this distance is dx, and this distance, let me take, this is along z direction, so this is dz. Okay, now we have another dimension that is along y direction, and this dimension is, let me take this dimension to be dy. So this cuboid is of volume d tau. I can write this volume V, this is dx into dy into dz. So what will be the area of this face? Area of this face will be dy into dz. You can see this dimension is dz. So the area ds. Okay, so this area, this is, I will write, this is dy into dz. Okay, now if you open up this, then you will get Ex1 into ds, that is dy into dz. Now at the first phase, you see the normal and the electric field, these are in opposite direction, so you will get here cos pi, and then plus Ex at the second phase. Okay, Ex at the second phase, and ds, the surface, this surface is again dy into dz, this is again dy into dz, and at the second phase you can see the normal and electric field, these are in the same direction, so you can write cos 0 degree. Okay, so this is how you will calculate the flux due to x component. Okay, so this will be, you see, cos pi, this is -1, and Ex dash, you see dy and dz, these are common, so you can take them out. Okay, and let me substitute the value of, here I will write dy into dz. Clear? This is the surface area, and the value of Ex1, this is this thing. So firstly, this is Ex, this is Ex, and you have plus curly Ex by curly x. Okay, here is minus sign, so we will write here minus, then you have dx by 2, you have dx by 2. Okay, it is half of the width of the cuboid along x direction. Okay, and then you have cos pi, so you have to put one more negative sign here. Okay, then you have Ex double dash, so now you have Ex2 at the second surface, so this is Ex and then plus curly Ex by curly x into dx by 2. Okay, so this is the value of Ex double dash. Then you have the surface area, this is dy into dz. Then you have cos 0 degree, cos 0 degree is 1. So now you have to solve this thing. So here let me clear this space. So if you solve this thing, then you will get the flux through the closed surface of the cuboid due to the x component, that will be equal to, you see here you can take dy dz common, okay, and you see here if you insert negative sign within the bracket, then you will get minus Ex and minus plus curly Ex by curly x dx by 2. Okay, so you see here Ex will cancel out and these two factors will add up, and this is dx by 2, this is dx by 2. So finally you will get curly Ex, I am writing it here, you will get curly Ex by curly x into dx. Okay, so this will be the sum of these two factors into dy into dz. Okay, so this is what you get after all calculation. And if you find the flux due to the y component, okay, here the surface will be, you see this surface is perpendicular to the x direction and this surface will be perpendicular to y direction. Okay, so this surface will be made up of dx and dz. Okay, and you will get here curly Ex, you can generalize, no need to solve like that. So I am writing here directly the result, that is dy, and here you will get dx into dz. Okay, and due to the z component you can find this thing, this was along perpendicular to y direction and this will be perpendicular to z direction, and here you will get curly Ez by curly z into dz, and the area will be here dx into dy. So the flux due to the electric field will be sum of the flux due to various components of electric field. So finally you can sum up all these things and you will get the flux due to the electric field E dot ds over the closed surface enclosing the volume V of the cuboid dx dy dz, that will be equal to, you see here you can take dx dy dz common, these are present in all factors, and within bracket you can write this thing Ex and plus you have curly y plus curly by curly z of Ez into dx, dy and dz. So what is this? This is the volume of the cuboid, and what is this factor inside the bracket? This is divergence. This is the divergence which we have written here, curly Ex by curly x plus curly Ey plus curly Ez by curly z. So this is the divergence. Okay, so what we can take idea from here, we can take the idea that this is the flux, this factor gives you the flux, okay, and this is equal to, this is what, divergence of the vector field, and this is what, this is the volume d tau, okay, or V, volume we have taken. So the divergence of the vector field, which is electric field here, that is equal to flux divided by volume, or flux per unit volume gives you the divergence of the vector field. Okay class, so this is how you can take idea of physical significance or physical meaning of divergence of the vector field. It is basically flux diverging out of the cuboid or the volume per unit volume, or you can write it flux density simply. And more about the flux, more about the physical meaning of divergence of the vector field we will understand in the next video lecture. Thanks for watching the lecture.